Hello everyone, welcome to Practically. We bring learning alive. We are discussing one-shot sessions for your class 9 term 2. As a part of that, math sessions as well as biology, chemistry and physics also. We have completed few gravitation topic in the last class, and today's session is on work and energy. Okay, in class 9 physics, if you see that science total composite of as we are having that science as composite in class 9, in that physics part we are having two chapters for your term 2 examination according to your NCERT syllabus. Already in the previous session gravitation we have completed, and now work and energy we are going to discuss. Okay, and am I audible? Whoever are watching, just respond. Is my voice audible to each and everyone? Am I audible, children? Just comment if audible, yes, if not, no. Okay, fine then. So see, the topic is work and energy, very important. In the previous chapter gravitation we are having numericals, even in work and energy also we are having so many numerical models. Various interesting topics are there, and this is the like a bridge I can say that bridge to your class 11, because the same chapter even in class 11 also we are having, that's work and energy and power we are having. Very important chapter in that mechanics part. Okay, so what topics that we are going to learn here are just like foundation, and extension to these topics you will be having in the higher grades. All right, fine. Here in this particular chapter we are going to learn about the name. If you look at once, work and energy, we are going to learn about work, what is meant by work done, what are its types. Okay, and energy, what is meant by energy, what are its types and law of conservation of energy. And then finally power, the rate of doing work, about the rate of doing work. So we are going to learn the outcomes of this chapter. If you strictly speak, then we can conclude it in three terms. One is work, another one is energy, and then power. Work, energy and power, that's what we are going to learn about. Okay, so let's start with our session with work, concept of work done. Okay, and as I said in the beginning, we are dealing with the one shots. Okay, for all the chapters, so-called mathematics, biology, chemistry and physics. Already gravitation we have completed on 17th Feb. Okay, and these are the dates that on which that one shots have done. Okay, so if you are having any doubts, you just go to that Practically YouTube channel on this particular day, what topic that we have done, that one short session has completed, you just go and watch that session. Okay, in that one single shot the entire lesson will be completed. That's how we have planned. So and now here today we are here 22nd Feb on work and energy, and then tomorrow and after tomorrow surface area and volume and probability. So mathematics topics are there. So tomorrow and after tomorrow the same timing you can have a mathematics topic. Okay, and apart from this, coding also going on. Yeah, it's done already, it's completed 2nd, 9th and 15th, 19th Feb. Okay, so to refer these topics, you can even these topics are already available in the Practical YouTube channel. Just go to the channel, subscribe that, and you can watch that. Okay, so then coming to the today's one, yes, work and scientific conception of work. Actually, work, it's a very important, interesting word. What is meant by work? A simple question. What is the meaning of the work in the physics? Actually, generally if I ask what is work done, you may say like I am doing that work, I am doing this work, I am reading a book, or else I am writing, or else I am walking, I am eating. All these things will be just like we'll feel that we are doing work, but that is what physical actions, what we are doing are physical actions, that writing or carrying something or else generally. So that physical meaning of work done is different, whereas physics, the meaning of work in the physics is different. Okay, I'll give a clarity here. Work and scientific conception of work. Generally, as I said, I am writing, it's a part of work. I mean, general conclusion, physical work done. But physical work done is different from physics work done. What is that scientific conception behind work? How can you define the work? Yeah, to define the work, here, when can we say the work according to science, according to physics especially? So we can say that work is said to be done if an object is displaced, if an object is displaced due to force acting on it, then work is said to be done. Work is said to be done. So see here, very important. When work is said to be done, yeah, NS Lucky, hi, Sparkling Star, good evening. If an object is displaced due to force acting on it, then work is said to be done. Suppose if you want to conclude there is a work done, that means that force should be acting on the body, as well as due to the force acting on the body should be displaced. If the body is displaced due to the force acting on it, then we can say that work is said to be done. So we can write the expression for work done as work is equals to force multiplied by displacement. Here W is equals to, if I represent F, I mean force with F and the displacement with the letter S, W is equals to F into S we can write. And when it comes to units here, SI unit of work done, if you see, that is joule, symbol is capital J, or you can write this as Newton meter also. Here, if you look at the unit ones, work done is equals to force multiplied by displacement. So 1 joule you can write it as 1 Newton multiplied by 1 meter. That means if an object is displaced to 1 meter due to the force acting on it is 1 Newton, then the work done by the body is said to be 1 joule. So 1 joule of work is done when 1 Newton amount of force acting on the body and if it is displaced through 1 meter. Alright, and then CBSE units on other hand, if you see, you can write it as erg. Erg is the CBSE unit of the work done, and one erg can be written as, it's 1 dyne multiplied by 1 centimeter, which means 1 dyne into 1 centimeter. And the relation between joule and erg is 1 joule is equals to 10 power 7 erg. These are the general relation between work done. Okay, work done, force and displacement. Work is said to be done if an object is displaced due to the force acting on it. Alright, and then we can write work done as force multiplied by displacement. So work done by a constant force, that's what we discussed here. Let us consider a body of mass m. So here, let F is the force acting on the body due to which the body is displaced to an extent S meter, let it be. Then here work can be written as force into displacement. W is equals to F into S. So this is what work done by the constant force. If F is the constant force acting on the body, which can displace the body to a displacement of S meter, then the work is said to be done. Work done by the constant force on that body can be written as force acting multiplied by the displacement. Suppose if let us discuss the same work done by the constant force through an illustration. There is an illustration here. That is, a force of 7 Newton is acting on an object. Object is displaced through 8 meter in the direction of the force. That's very important. It's displaced in the direction of the force. If the force acts on the object all through the displacement, so force is acting on the body constantly throughout the display, all through the displacement. What is the work done in this case? Simple here. So first I am writing the given data. What is given here? Force acting on the body is given. How much force is acting on the body? 7 Newton amount of force is acting on the body. And then displacement of the body is given. Displacement is equals to 8 meter. So how can we write work as? Work is equals to, just now I said it is force multiplied by displacement. In terms of force and displacement, you can write it as product of force and displacement. And then here 7 multiplied by 8, 7 8s are 56. And then as we have to specify the unit here, since the work done will be having units, so it is 56 joule. Alright, so this is how we can calculate this kind of model. So this model will come under work done by constant force. Okay. Next one, types of work done. Very important one. So here, based on the displacement, how the displacement and force directions are related, based on that, work done by the body is classified or is segregated into 3 types. So there are 3 types of work done in general. What are those 3 types of work done? One, that is positive work done. Secondly, negative work done. And third one, zero work done. Let us discuss one by one. Positive work done. Suppose let an object which is having certain mass on which a force F is acting, and due to that force, if the body is displaced through a distance S meter. Now see here, the direction of force on which the body, on which it is applied, is taken in this direction, and in the same direction if the body is undergone for displacement, then the work done is said to be positive work done. See, I am repeating the statement. If the displacement of the object and the direction of the component of force are in same direction, then work done is said to be positive. Force is applied on the body in this direction, and the body is suffered to the displacement in the same direction. So we can say that work is done, and that work done is positive, since both the force and displacement are in the same direction. Suppose in the same example, if you see here, object has suffered to a displacement in this direction due to the force applied F, but at the point of contact, okay, if I say this frictional force will be acting in the direction opposite to the relative motion of the body. So it's a general known one. Yeah, Abhinava. Hi, Abhinava. So in this case, when this force F is applied on the body and the body is undergone for this displacement, at that time frictional force also acting on the body. So if you are talking about the work done in the point of applied force, then work done is positive, since the direction of the force applied as well as the direction of the displacement in which the body has suffered, both are in the same direction, so work done is positive. But the same case, if I talk about, if I'll discuss in the point of frictional force, displacement suffered in the point of frictional force, if you see, the direction of the frictional force is acting in opposite direction to the displacement caused. So here work done is said to be negative. So very simple, when work done is said to be negative, if the component of force acting on the body is opposite to the direction of the displacement along which it is suffered, then work done is said to be negative. If the component of force acting on the body is same as the direction of the displacement along which it has suffered, then work done is positive. Positive work done if force and displacement are in the same direction. Negative work done if the force and displacement are in opposite direction. And zero work done. For zero work done, there are some different possibilities. First one, suppose if there is no force acting on the body, then work done is zero. Since work done is equals to force multiplied by displacement, there is no force, there is no displacement, there is no work. Second case, force acting on the body but displacement is not there. If displacement is zero, then also work done is zero. Just like if I am pushing the wall, okay, to push the wall I have to apply very huge amount of force. Okay, generally I am pushing the wall, but the force what I am applying on the wall is not sufficient to displace it. So force is acting on the body, but the body is not displaced here. Displacement zero, still force is there. Then also work done zero. So if force is zero, work done is zero. Or else if displacement of the body is zero, then also work done is zero. Alright, next. If force and displacement act at right angles, then also work done is said to be zero. So what does it mean? Suppose a porter is carrying luggage by placing on his head. Okay, so in such case the weight of the object is acting downward. So weight is a kind of force, and the body has suffered displacement in this direction. Suppose, say, how displacement and force are acting here? They are acting at right angles. So in such case work done can be written as 0 joule. Okay, so displacement direction as well as the force direction, if both are acting at right angles, then also work done is said to be 0. So in what cases, under what cases 0 work done can be possible? Under these three cases: if force acting on the body is 0, work done is 0. If the displacement cost is 0, then also work done 0. And if both force and displacement are acting at right angles, then also work done is 0. Positive work done, negative work done, 0 work done. Alright, so these are the types of work done. Okay, let's move on to the next topic. Yeah, there is a question here. A porter lifts a luggage of 15 kg from the ground and puts it on his head 1.5 meter above the ground. Calculate the work done by him on the luggage. Okay. Okay, see here. Porter lifts a luggage of 15 kg from the ground and puts it on his head 1.5 meter above the ground. Suppose if this is the ground, he had kept the luggage at this height. Now see, to lift the object, he has to apply some force on it. The minimum force that he has to apply on the body to lift it is the weight of the body. So say if W is the weight of the body, weight W is acting downward. Okay, the same box here if I take, that will be acting downward. By applying that minimum amount of force, he can lift the body. Alright, so work done is equals to, as we know, it is force multiplied by displacement here. How much weight he has to how much force he has to apply, that equals the weight of the body. So the force here is nothing but weight of the object. To what height it is raised up, that is the displacement caused. So height. Weight, how it can be written as, it's it's a mass multiplied by acceleration due to gravity, and height h. So m value it's given as 15 kg, g is not given, take 10 meter per second square, h value is 1.5 meter, 15 into 10 into 1.5, this is 15 again, 15 15s are 225. So 225 joules of work is done to lift the body from ground to a height of 1.5 meter. So that is how you have to solve this type of question. All right. So let us see the next one. Yeah, energy. Okay. What is meant by energy? Let us see. We all know energy is existed in various forms. Okay. So in general, the definition of energy can be written as capacity to do work. The capacity to do work or the ability of doing work. The capacity of to do work or the ability of doing work is called energy. Okay. Here the units of energy is just similar as units of work done. Okay. Units, SI unit of energy is joule and CGS unit of energy is erg. As I said already, 1 joule is equals to 10 raised to 7 erg. Okay, and this energy will be existed in various forms. Like a few of the forms of energy, let's see here. Light is a form of energy, heat is a form of energy, electrical energy is there, sound also is a form of energy. Next, chemical energy. Okay, nuclear energy. The list goes on. Since it's existed in various forms, whatever we are seeing, suppose here we are able to see the objects with the help of light. Light is a form of energy. And heat is a form of energy. Sound, what we are listening generally, that listening sensation, sound is a form of energy. Nuclear energy, electrical energy, geothermal energy, tidal energy, chemical energy, wind energy, solar energy, like that, that list goes on. So energy is existed in various forms. Okay. So then let's talk about kinetic energy. So here in this particular topic in class 9, especially we are having the format of mechanical energy. Actually mechanical energy is the sum of both kinetic energy as well as potential energy. I mean, we can represent it may be either purely in the form of kinetic energy or purely in the form of potential energy, doesn't matter. So mechanical energy we can represent in terms of both kinetic energy as well as potential energy. Now let's talk about kinetic energy. Yeah, titanium sir, aap kahan se? From Hyderabad. Okay. How are you doing, titanium? Okay. So see here, kinetic energy. So let us see the definition and further we will derive the expression for it. Kinetic energy can be defined as energy possessed by the body by virtue of its motion. So see here, the energy possessed by the body by virtue of its motion is called kinetic energy. All right. Suppose let us consider an object which is having a mass, which is having such mass m. Initially, let the object is under rest position. Say its initial velocity is 0 meter per second. And now, say if amount of force is acting on the body, that force further caused a displacement s. That the displacement caused in the body due to the force applied on it is s. Say the velocity of the body is changed to v meter per second at the after traveling a displacement s meter. So here it's very clear the body has undergone for displacement due to the force acting on the body, that to the direction of the displacement as well as the direction of the force acting on it, both are in the same direction. So we can say that work is said to be done and the work done is positive here in this case. Okay, so work done can be written as force multiplied by displacement, which is the known thing. W is equals to, we can write it as force multiplied by displacement. Okay, on another hand, you can see here in this particular case, the object, it is traveled in the straight line direction and its velocity is changed from 0 meter per second to v meter per second. There is a change in velocity with respect to the time. So the rate of change of velocity, what we are calling it as acceleration. So here the body is traveled with uniform acceleration. So in class 9, in the same in the 9th class, we are having motion chapter. Term 1 you have learnt. Okay, in motion you have studied about equations of motion, which you have deduced with the help of graphical method. Okay, so there, that equations of motion you can apply wherever the body is traveling with uniform acceleration. In this particular case, body has undergone for uniform acceleration. Here you can check straight line motion, its velocity changed from at the uniform rate. So you can apply the equations of motion. I am recalling the suitable equations of motion, that is v square minus u square is equals to 2as. So here, as I said, initial velocity is 0 according to the assumption, and this is v square is equals to 2as. So v square, how can you write that as here? V square by 2 is equals to as. Okay, keep that in mind. And now here, according to Newton's second law of motion, how can we write the force? W is equals to, force can be written as mass multiplied by acceleration, ma into s. And here you can see m into as means what? It's a v square by 2. So here we are having it as half mv square. And now whatever the work that is done on the body or done by the body here, that will be stored in the form of some energy. What energy here? That energy here, it is possessed because of its motion, and that we are calling it as kinetic energy. So kinetic energy is equals to half mv square. Whatever work that is done will be stored in the form of kinetic energy, and that can be written as half mv square, and this is how you can derive an expression for kinetic energy. Okay, fine. Yeah, there is a question on this topic. See here, an object of mass 15 kg is moving with a uniform velocity of 4 meter per second. What is the kinetic energy possessed by the body? So we have to find out kinetic energy. Just now we have obtained the expression for it. Kinetic energy is equals to half into mass into velocity square. So here we can write it as kinetic energy is equals to half into mass of the body, that is given 15 kg, multiplied by velocity is 4 square. 4 4s are 16. 16 by 2. Here we'll get 15 multiplied by 16 by 2. 2 1s are 2, 8s are 15, 8s are 120. So 120 joule is the kinetic energy possessed by this body. Okay, so you can solve this model with the help of kinetic energy formula like this. Next one, work energy theorem. Very, very important. Work energy theorem states that, here statement is there and followed by statement, you have to deduce an expression for it. Very important and very easy also. Kinetic energy derivation you have learned, right? In the same process, similar process, we can state and prove work energy theorem also. So when it comes to statement, work energy theorem states that work done by the force acting on a body work done by the force acting on a body is equal to change in its kinetic energy. Change in its kinetic energy. What does it mean? Suppose say an object which is having mass m is traveling with initial velocity u meter per second, and let a force F is applied on the body, due to which the body has suffered to a displacement S. Okay, further, and let the velocity of the body has changed to V, from U to V. Then the initial kinetic energy, here Ke initial, what can we write? Half mu square. Similarly, Ke final, what can we write? Half mv square. So work done is equals to here change in kinetic energy. How can we write that? Final kinetic energy minus initial kinetic energy. That means half m into v square minus u square. This is what work energy theorem is stating. Work done by the body is equals to change in kinetic energy. So let us see how can we prove it. This description is same as it is. Consider an object having mass m which is traveling with certain velocity. Let's say initial velocity of the object is u meter per second. If amount of force is acting on the body, and then the velocity has become v meter per second, there is a change in the velocity from u to v meter per second, and it has happened a uniform rate, then we can say that body is said to be accelerated. Since the rate of change of velocity, we are calling it as acceleration. As there is uniform acceleration here, we can apply equations of motion to this one. So we know that equations of motion, according to the equations of motion, third equation of motion, which we are calling it as the velocity and position relation, v square minus u square is equals to 2as. So we can write here v square minus u square by 2 is equals to a multiplied by s. Keep that aside, and here it is very clear, force is acting on the body and the body has suffered to the displacement s. Of course, the direction of displacement here is along the direction of the force acting on it. We can say that positive work is done, and the work done can be written as here force multiplied by displacement, of course. Then force, according to Newton's second law, we can write the expression for force as mass multiplied by acceleration. So it will be MAS. So then m multiplied by a into s, we can write it as v square minus u square by 2. So then w is equals to half m multiplied by v square minus u square. So you can see here w is equals to, so this is what we have extracted here, half m v square into half m into v square minus u square, the same you can see here. So we can write this as half m v square minus half m u square, which further can be written as Ke final minus Ke initial. That means work done is equals to change in kinetic energy. So this is what the statement, work done is equals to change in its kinetic energy. Work done by the body, work done by the constant force acting on the body is equals to change in kinetic energy, and the proof will be like this. If you are given this in the examination, you have to give the statement and you have to prove it. Proving is very simple, just like this. Okay, and suppose, and see, if you look at this derivation once again, if you replace the velocity initial, I mean if you imagine the initial velocity is 0 here, that means here it will become this will become w is equals to half mv square, which is the same derivation that we have learned previously for kinetic energy. All right, now see here, there is a question based on this work energy theorem. What is the work to be done to increase the velocity of a car from 54 km per hour to 72 km per hour if the mass of the car is 1500 kg? All right, the body is, I mean here the body, in the sense the object here it is car. So car is already traveling with initial velocity which is 54 km per hour, and that velocity is changed from 54 to 72 km per hour due to what? Okay, fine, due to certain force. Even force is not given, no issues, leave it. And mass of the body is 1500 kg. What is the work done in this case? So far we have dealt like work done calculation. Work done is equals to force multiplied by displacement. we have written the work done in terms of force and displacement. But here in this particular case, there is no force acting on the body, and you are not given even the displacement that has caused here. I mean, the displacement occurred. Displacement value is not given, force is not given, and still you are asked to calculate work done. So let us recall any other method is there. Yeah, if you look at this one, work to be done to increase the velocity from x value to y value, or one value to another value. So work is done to change the velocity of the body from one certain value to another certain value. That means here body is under motion, as it is having it's having some initial velocity, so it's having initial kinetic energy, and its velocity is changed, it will be having final kinetic energy. So you can write this, you can solve this by using work energy theorem concept. So work energy theorem, what we have learned in it, work done by the body by the constant force acting on the body is equals to change in its kinetic energy. Change in its kinetic energy. That means half mv square minus half mu square. So here initial velocity and final velocities are given. Initial velocity is equals to 54 kmph. It is kilometer per hour. And one of the important point that every children has to remember while solving numericals, especially in physics, is what? After reading the question, you have to cross check whether the given physical quantities are they under same unit system or else different one. If they are in same unit system, you can proceed to solve. But if they are in different unit system, then make sure that all the physical quantities, you have to make them in a common unit system. Whatever, whether it is SI system or CBSE system, doesn't matter. Okay. So 54 kilometer per hour, mass is given 1500 kilogram. That's in SI system. SI unit of mass is kilogram, and then I am converting this kilometer per hour into meter per second, which is the SI unit of the velocity or speed, whatever. So here 54 multiplied by kilometer per hour can be converted into meter per second by using a multiplication factor, that is 5 by 18. 18 ones are 18 threes are 3 5s are 15, so u value is 15 meter per second. This is initial velocity. Okay, similarly final velocity is v is equals to, it is 72 kilometer per hour, and then it can be written as 72 multiplied by 5 by 18. 18 ones are 18 fours are, so 4 5s are 20. Final velocity is 20 meter per second. So the velocity is changed from 15 meter per second to 20 meter per second. And then here, if you substitute here in this formula, this is half m multiplied by v square minus u square. This you can write like this. That is equals to 1500 divided by 2 into 20 square multiplied by 15 square. So this is 750. 20 20s are 400, 15 15s are 225. 400 minus 225. So 200 or 25, 175. 750 into 175, which further gives 131250 joules. Okay, it's an example question from the textbook, so directly I have written. Yeah, Mukura Vijay Kumar, hi. Hi Sona, fine. If you are new, then no problem. Whatever the topics that if you are having any doubts, then you can just watch the previous videos. The same like this, the previous sessions also are uploaded on the YouTube. All mathematics, chemistry, physics, as well as biology. Yeah. So see here, we got here 131250 joule. This question we have solved by using work energy theorem. The earlier questions to calculate work done, we have applied force and displacement, but there is no force, there is no displacement. Still we have calculated work done with the help of work energy theorem. How the work energy theorem has applied, you can see here. This is the statement and proof for it. Okay. Yeah, what you can multiply 175 to 75, then what will you get? Yeah, this chapter is work and energy, class 9. Okay. You can multiply here. What will you get? 175 1500 by 2, right? 750, no? Okay, sorry, it's 138250, no? 138250. Who is that? Abjal. 750 multiplied by 175. 175 into 750. Oh, 5 5s are 25 here. Sorry. Sorry, just a minute. I think calculation is wrong here. Just a minute. It's correct only here. 131250. It's correct, 131250, which I have written earlier. That is correct only. You can calculate, you can check. Half m v square minus u square. M value 1500, 1500 by 2. 1500 by 2 is 750, right? V value 20. 20 20s are 400. U value 15. 15 15s are 225. 400 minus 225 will be having 175. 175 into 750, that is 131250. Okay. Yeah, fine then. Next one, potential energy. Potential energy can be defined as, in the kinetic energy, we defined it as the energy possessed by the body by virtue of its motion. Okay. It's not right. It's right. Okay. Fine. Very good. Potential energy can be defined as energy possessed by the body by virtue of its position. Earlier kinetic energy we have seen, it's defined as by virtue of its motion. Now it's by virtue of its position or configuration. Okay. Energy possessed by the body by virtue of its position. By virtue of its position is called potential energy. Suppose if I say an object is lying on the ground, with respect to the ground, the reference point is very very important here. With respect to what? So with respect to the ground level, the height at which the body is located is 0 meter. So the potential energy possessed by this object with respect to the ground is 0 joule. If I take the same object from here, from ground level to certain height h, now what will happen? There is a change in its configuration with respect to the ground level. There is a change in its position with respect to the ground level. So we can say that the body here can possess certain amount of energy. That energy will be stored as potential energy. Ashri Kumar, hi. Yeah. So then here potential energy is nothing but energy possessed by the body by virtue of its position. So now this object, when it is taken to a height h with respect to the ground, what we have to do certain work. Obviously whatever the work that we are going to do, that will be stored in the form of energy. That energy only potential energy here. So now here if you see, potential energy of an object at a height. So if the same object, in the previous case, I have taken an object which is having certain mass to a height h with respect to the ground level, then I said it possesses some energy, that is potential energy. How much potential energy that can be possessed, let's going to calculate here. Let's calculate. See here, say initially the object is lying on the ground where its potential energy is 0. Now it's taken up and it's placed here, and now here you can see here, let the displacement covered by the body is h. See the weight of the body which is acting downward. If you want to lift the body here, if you want to lift the object, then you have to apply the minimum force on the body which is equals to weight of the body. Okay, so then I can say work is equals to force multiplied by displacement here. How much force that you have to apply on the body, which is equals to weight of the body, multiplied by displacement is nothing but through what height the object is raised, that will be the displacement here. So weight of the body, we know that it is mg, height is h, so work is equals to mgh. Then here you can write mgh, right? This is the amount of work done to displace it from here to here. That work will be stored in the form of potential energy. So therefore potential energy here in this case can be written as mgh in this particular case. Here two things, is that work is positive work done or negative work done. Again I am saying to classify or to say that work is positive or negative, you have to remember that important point, that is you have to check whether the direction of the displacement and force are they in same direction or opposite direction. If the direction of the displacement as well as the direction of the force acting on it are in the same direction, then positive work done. Opposite direction, then negative work done. Here in this case, if I am talking about the applied force, okay, if I want to place the object from here to here, I have to lift the body by using some amount of force in this direction, like say applied force. So applied force as well as the displacement are in same direction. The work done by the applied force in this case is positive. In the same example, gravitational force will act downward. So work done by the gravitational force is negative, since the body is lifted here against the gravitational force. Alright, just like that. Hope you have understood. I am saying here, to decide the work here is positive or negative, you should think about in which force point of view we are discussing. If we are discussing the applied force point of view, work done is positive, since the displacement is happened here in the direction of the force. Whereas if you are discussing the point of gravitational force, as the displacement of the object is opposite to the gravitational force acting here, so we can say that work done by the gravitational force is negative, right? So there is a question on this topic. Let us see. An object of mass 12 kg is at a certain height above the ground. If the potential energy of the object is 480 joule, find the height at which the object is with respect to the ground. G is equals to 10 meter per second square is given. So they are asking here, when the object is lifted to a height h, the potential energy stored in the body is given, that is 480 joule. Then what is the height? That's what the question. Find the height at which the object is with respect to the ground. So potential energy stored here is given, that can be written in terms of mass and height as mgh. How will it be? Just now we have derived. And potential energy can be written here as 480 joules, since it is given in the question itself. And then mass of the body is 12 kg, G value is 10 meter per second square, h we have to find. Then height to which it is raised with respect to the ground can be h is equals to 480 by 12 multiplied by 10. So 1 0 1 0 cancel, 12 4s are 48. So height h is equals to, 12 4s, yeah, it's a 4 meter. So at 4 meter height the body can possess 480 joule. Yeah, Ashri Kumar, this is one shot session, and the chapter what we are discussing is work energy from class 9. Okay. Alright, so this is the question that's based on the potential energy acquired. Yeah, another important one, law of conservation of energy. Very important. Okay, so the single and straight statement to define law of conservation of energy is law of conservation of energy, conserved. What quantity is conserved here? Energy. Energy is conserved, which means energy remains constant. Energy is unchanged or remains unchanged. So how can you define that? Very simple way. Law of conservation of energy states that energy can neither be created just a minute. It states that energy can neither be created nor destroyed. But it can be converted from one form to another form, and the total energy remains constant. See here, very important one. Yeah. Okay, Sona, fine then. See here, law of conservation of energy. Energy can neither be created nor be destroyed, but it can be converted from one form to another form, and the total energy remains constant. Alright, so here generally if you look at the statement once, we can't create the energy, it's a fact, we can destroy it, but what all we can do is we can convert it from one form to another form based on the requirement. Like I can say, suppose if you want light here, we'll use a device called bulb. Bulb converts electrical energy into light energy. So based on our requirement, here we are using light. It is taking electrical energy as input and it's giving light energy as output. Suppose if you want sound energy, like if you want to ring any bell, electric bell, so their electrical energy will give as input, and further it can that will be converted as sound energy. So based on the requirement, energy conversion can be happened here. We are not creating and we are not destroying, we are just converting it from one form to another form. Alright, fine. And the total energy here remains constant. That's what the very important one, so that we can say that it's conserved here. And the best energy and best example to explain this conservation of energy is, we all used to think like electrical energy. Suppose best example, electrical energy, from where we are getting this one. Actually here electrical energy is not being created, it's not being created, it's being converted from one form to another form. How it will be? So I'll say, you might have seen this reservoir, storage of the water in the dam or reservoir. There you can see that power station where this electrical energy will be converted with the help of so and so arrangements, like turbine, mechanical turbine as well as generator arrangement will be there, right? So there the water will be stored in that reservoir or dam at greatest height, due to which the water can possess potential energy, hydrostatic potential energy. It has possessed by default. No one has given that energy to the water. Just because of its position, by nature, by default it has possessed it. And that potential energy, when that water is made to pass through large pipes, so called that penstocks, now that water is in motion, so potential energy will be converted into kinetic energy. That water will make certain arrangements to hit the turbine vein of the turbine or wings of the turbine. So now turbine will rotate. To the turbine, generator will be coupled. So turbine will be rotating. As a result, that generator also will rotate. So generator is taking mechanical energy as input, this from which we are getting here from turbine, right? And that one from the water hitting. So mechanical energy is given as input to the generator, and further generator converts that mechanical energy into electrical energy. So nowhere else here you have given the energy by someone else or by additionally or by external source. It has been possessed by the water by default, and that energy we converted into the required electrical energy. So what formula that we have applied here? This only conversion formula, converting that energy from one form to the required form. And whereas in this total system, total process, if you think, there is no wastage of energy here. Wastage of energy in the sense, if you want electrical energy, as if you are feeling it as useful, you may think that remaining wastage of water that may causes the wastage of energy, but that will be existed in the form of another energy. All right, so here there is no word called wastage of the energy. It has not lost, it is existed in some other form. Suppose if you are giving some 100% of mechanical energy, let's say the output of that mechanical energy is some 40% or 50%. The remaining output will be in some other form. If not electrical energy, that will be in some other form. So we can say that here, yeah, so we can say that electrical energy is the energy can be converted from one form to another form, and the total energy remains constant. Energy can either be created nor be destroyed. Overall energy remains constant. That's what we are calling it as law of conservation of energy. All right, right. So now let's prove this conservation of mechanical energy of a freely falling body. Very, very important. There is a freely falling body. For that body, mechanical energy remains constant. Let's prove it. Okay. So consider an object having mass m is released freely from a height h with respect to the ground. When the object is at this height, this will be having potential energy. How much potential energy? Say mass of the body is m, acceleration due to gravity g, height h. So potential energy of this object when it is at this height with respect to the ground is mgh. All right. Now, as I said, this is a freely falling body. When the object is under free fall, we have learnt in the gravitation, when the object is under free fall, it will travel under the influence of the gravity. So here the initial velocity is 0, and at this point, what is kinetic energy? 0. So how can you write this mechanical energy? Mechanical energy you can express in terms of both potential energy as well as kinetic energy. So mechanical energy can be here, potential energy is mgh and kinetic energy is 0. So mechanical energy is equals to mgh. Now we have to prove the mechanical energy will be the same throughout the path along which the object has traveled. You may take this point or some other points, but the total energy always mgh. So already at this point, say the point here it is A, and randomly some other point B and some other point C I am taking here along its path. So if you are able to prove the mechanical energy mgh it remains the same even at point B and point C, the law of conservation of energy is obeyed here. Okay. Okay, class key timing 6 to 8. Sona, it's 6 to 8. Right, say the object is traveled from A to B a distance x, and the remaining distance will become h minus x. So this is at point A. We have calculated already. At point A is mechanical energy mgh. Now say at point B here, at point B the object is over here, which is at a height of h minus x with respect to the ground. So potential energy can be written as mg into h minus x. When the object is at this height, as height is h, we have written potential energy is mgh. Now object is here, so then height is h minus x, so potential energy is mg into h minus x. Then it will become mgh minus mgx. On other hand, as the body is now at point B and it is in motion, it will acquire certain velocity at this point B. So we can say that the body will be having kinetic energy. So that kinetic energy can be written as Ke is equals to half mv square. Say velocity of the body is v square over here. Okay. So then we know that v square minus u square is equals to 2as formula I am applying. v square minus initial velocity of the body is 0 square, as it is traveling downward, so replace a with g, and displacement covered by the body from a to b is x, so v square is equals to, it's 2gx, substitute here, kinetic energy is equals to half m into 2gx, 2 get cancelled, so it is mgh. Okay, then mechanical energy is equals to potential energy and kinetic energy summation, so we can write here mgh minus mgx plus mgx, both these mgx terms will be cancelled and will be having mgh here itself. So see here, even at point B also total mechanical energy is mgh. Remember here air friction we are regulating it. Okay, next one, at point C here, so what will happen at point C? At point C now the body is on the ground, it will reach this position, so there is no minimum, I mean the height at which the body is located here will become 0 with respect to the ground, since it is lying on the ground. So then at point C potential energy is 0, straight point that is, and then kinetic energy can be written as half m, say the velocity at the point C when the body is about to touch the ground, say its velocity v dash, so half m v dash square. Alright, then ke is equals to half m, what is v dash square? How can we extract v dash square? Here a simple calculation for it. We are having that formula, v dash square minus u square is equals to 2as. Equations of motion I am applying. V dash square we are calculating, u is 0 and this will be 2gh. Since from here to here I am taking the reference now, and the displacement covered from A to C is h here, so v dash square value 2gh, then half m into 2gh, 2 get cancelled, kinetic energy is mgh here, so mechanical energy can be written as 0 plus mgh, therefore mechanical energy will become mgh. So now you can cross check, at point A mechanical energy mgh, at point B it is mgh, at point C it is mgh. So throughout its journey the mechanical energy of the body remains the same. This proves law of conservation of energy for a freely falling body. Very important derivation and easy also. Okay, so next one, rate of doing work. What is meant by rate of doing work? The rate at which work is done is said to be power. Okay, power can be written as rate of doing work. That means power is equals to work done by time. Okay, and even we can write this as power is equals to energy by time. And for energy we can say here energy is equals to, how can we write, if you bring time to this side, energy is equals to power multiplied by time. Remember this formula, while we are solving that electrical energy bill calculation we have to apply this only. Okay, and in terms of force and velocity we can say power is equals to force multiplied by velocity. Force multiplied by velocity will be giving power of the body. Okay, and here units, if you look at once, SI unit of power is watt. 1 watt is equals to, symbol you can write it as capital W, 1 joule by 1 second. If 1 joule of work is said to be done in 1 second, then power either delivered or power consumed by the body is 1 watt. 1 watt is equals to 1 joule by 1 second. Okay, and CBSE unit of power is, it is erg by second. Okay, these are SI unit and this is CBSE unit of the power. Here another important point is, these are the general units of the power, but commercial unit of power is there. Commercial unit of power is horsepower, which you might have known already. horsepower, we'll call it as HP. 1 horsepower is equals to 746 watt. Okay. Similarly, how there is a commercial unit for power, there is a commercial unit for electrical energy, that is kilowatt hour. Okay, very important. Kilowatt hour, we can say it as kWh, is commercial unit of electrical energy. Commercial unit of power is horsepower. 1 horsepower is equals to 746 watt. Commercial unit of electrical energy is kilowatt hour. 1 kilowatt hour can be written as 3.6 into 10 power 6 joule. Okay, very important one. Mohan Prashant, this is a class 9. Yeah, Anjali 746 watt, that is correct. Okay, this is class 9 physics, work and energy chapter. Okay, we are having a question on power. Let us solve this. A boy of mass 50 kg runs up a staircase of 45 steps in 9 seconds. If the height of each step is 15 centimeter, find his power. Take G value 10 meter per second square. Alright. Just now we discussed power can be written as work divided by time. Power P is equals to work by time. This is the W by T. Power P is equals to work value we have to find. Here the boy runs up a staircase. So staircase will be like this. So finally here let it be. Alright, each step height is 15 centimeter. Totally there are 9 steps. So this is the height with respect to the ground. Finally the boy reached this one. So say the boy is there. So height covered by the body is equals to, if each step height is 15 centimeter, sorry 45, what is it? Number of steps 45, sorry. Okay. So number of steps 45. Each step height is 15 centimeter. At that time when he reaches the final one, this will be the height. So we can write it as 15 multiplied by 45, which gives 75, 60, 67. Okay, it is 675 centimeter. But while we are writing, as I said already, while you are solving the numericals, you should make sure that all the units of the physical quantity should be in a common system. Already here this G value is in SI system and M is in SI system. Say this H is 675 meter, you can convert into meter. So then height H is equals to 675 by 100, that is equals to 6.75 meter. So work done can be written as mgh by time t. Since work done is equals to force multiplied by time, from here to here he has to lift up his own body. That means his own weight he has to overcome. Weight of the body is mg, and height to which he has to rise is h. So mgh by time t. Okay. So then m value it is 50, G value 10, H value 6.75 divided by 9. Simplify this, you will get 375 watt. Okay, and that will be correct. Okay, Sona, that will be the correct one, don't worry. Next one, there is a question on electrical energy calculation. An electric bulb of 60 watt is used for 6 hours per day. Calculate the units of energy consumed in 1 day by the bulb. So energy calculation very important. Yeah, Athar, good evening Athar. Electrical energy, commercial unit of electrical energy is kilowatt hour. While calculating this in units, one hint you have to remember, that is 1 kilowatt hour is equals to 1 unit consumption. 1 unit consumption of electrical energy can nothing but 1 kilowatt hour. Kilowatt hours joule means 3.6 into 10 power 6 joule, that is different. But in terms of the units, if you want to represent this electrical energy, first you have to calculate in terms of kilowatt hour. Then how many number of kilowatt hours you will get, that many number of units of consumption is happened. Okay, so power P is equals to, we know that it is energy by time, and then we can say here energy is equals to power into time. All right, there is only one device in this particular question, that is electric bulb, which is having a power 60 watt. So power is 60 watt and it is operated for 6 hours per day. Calculate units of energy consumed in 1 day. They are asking for 1 day. So 60 here multiplied by the day, 6 hours. 6 6 are 36. So it is 360 watt hour. But you are asked to calculate in number of units. Number of units, if you want to know units, you should know how many kilowatt hours consumption. But this is in watt hour. Then convert it into kilowatt hour by dividing it with 1000. Then you will get 360 by 1000 kilowatt hour, which is 0.36 watt hour. Sorry, 0.36 kilowatt hour. 1 kilowatt hour is equals to 1 unit. Therefore, it will become 0.36 units is the consumption of the energy. Suppose if the same question you would have asked for to calculate 30 days or 1 month, then you should multiply this 0.36 with 30. Since this is the calculation of energy for 1 day, 30 days means multiply with 30. Sometimes they mention the name of the month because all the months won't be having the same number of days, right? Like February it is, and even except the other than the leap year, it will be having 28 days. September 30 days, October 31 days. So depend on the month also, you have to change the number of days. So be careful. Yeah. So it's not 360, it is 0.36. Okay. Since 360 by 1000 will be having 1, 2, 3 decimals, you have to shift. Sona, it is 0.36 kilowatt hour, nothing but 0.36 units. Okay, Sona, fine. Yeah, all right. And this is what the today's session is about. Okay. So if you are having any doubts, then you just watch the video once again. And still, if you'll be having any doubts, just download the Practically app. There's an option called Seek Help Team. You just raise your query or doubt, whatever that you'll be having, so that you can get it clarified. All right. That's all for the day. Thank you all of you. Signing off.